Today, we're pushing past that familiar picture of the cosmic microwave background, that baby picture of the universe. We're going to dive deep, really deep into its spectrum. It's a place where, well, the tiniest little deviations can give us clues about events that happened even before that first light even appeared.
Yeah, it's amazing, isn't it? The CMB spectrum, it's almost a perfect black body, it's like a cornerstone of the Big Bang model. But the really cool stuff, the real intrigue, it's hidden in these tiny imperfections. They're called spectral distortions, and they whisper, literally whisper, stories about the universe's very beginnings, like a chaotic, wild beginning.
Spectral distortions, huh? It's like
Yeah.
I don't know,
Uh,
blemishes on a perfect canvas. But you're saying they're not really flaws.
No, no, not at all. These distortions, I mean, they're tiny, sometimes only one part in like 10,000, but they're so valuable, like relics from the past. They hold information about energy shifts, particle interactions from epochs we can't even observe directly. It's incredible.
Okay, so as we get into this deep dive, let's start with the basics. Can you break down the idea of the CMB as a black body? What makes its spectrum so special?
All right, imagine something, an object that absorbs all radiation hitting it, every single bit, no matter the frequency. And this object, it would also emit radiation, and the spectrum of that radiation would be determined only by its temperature. That's black body radiation in a nutshell. And the CMB is like the poster child for it.
And the CMB spectrum, it aligns like amazingly well with this theoretical idea,
Oh,
right?
yeah, incredibly well. We got these measurements from the Kobe satellite back in the 90s, and they showed just how close the CMB spectrum is to a perfect black body. A perfect black body at a temperature of about, let's see, 2.7255 Kelvin. And that agreement, it's one of the strongest pieces of evidence for the Big Bang model. It's really remarkable.
So with such a good fit, you might wonder why even bother looking for deviations, these spectral distortions, right?
Yeah.
I mean, if it's that close, shouldn't that be the end of it?
Well, that's where the thermalization problem comes in. It's a bit of a head scratcher. You see, while the CMB spectrum is an incredible black body, it shouldn't be absolutely perfect. Any energy release, any change in the number of photons in the early universe, however small, would have left a mark, a tiny signature, on the CMB spectrum. So the question becomes, how did the universe get so darn close to equilibrium, given all the crazy stuff happening early on?
The thermalization problem. So not so much a problem as a fascinating mystery, right?
Exactly.
Yeah.
It makes us dig deeper, try to understand how the CMB got to be such a pristine black body. We're talking events like decaying particles, those primordial density fluctuations smoothing out, even that epoch of primordial recombination, they all messed with the energy of the primordial photon bath.
So the fact that we see this smooth, near-perfect black body spectrum tells us there must have been something smoothing out these distortions.
Absolutely. And that's where Compton scattering comes in. This process where photons interact with free electrons, it's like a cosmic smoothing iron. Think of it like a giant game of cosmic billiards, photons bouncing around, redistributing their energy, smoothing out the wrinkles in the CMB's spectrum.
Compton scattering a cosmic iron, huh?
Yeah.
I like that, smoothing out the wrinkles in the CMB spectrum.
Hmm.
That's a pretty good analogy.
Yeah, I think it gets the point across. But there's a catch. Compton scattering is great at moving photon energy around, but it doesn't change the total number of photons. To get to a real equilibrium, a true black body, we need things that can create or destroy photons.
So what are those things? What controls how photons are created and destroyed in the early universe?
There are two main players, double Compton scattering and Bremsstrahlung. Bremsstrahlung is, well, it's also known as free emission, happens when charged particles slow down and spit out photons. Then there's double Compton scattering, which is a kind of correction to the regular Compton scattering where an extra low-energy photon gets created.
So we have all this happening at once in the early universe. Energy being added, photons scattering, photons being created and destroyed. That leads to the question, what kind of distortions should we expect to see in the CMB spectrum?
That's where we start categorizing these spectral distortions. We can broadly group them into two main types, Yai distortions and mood distortions.
Yi and Mu.
Yeah.
Sounds like we're getting into some physics alphabet soup here.
The names might seem a bit strange, but the ideas behind them are pretty profound. Yai distortions pop up when the energy exchange between those photons and electrons through Compton scattering is inefficient, meaning there aren't that many scatterings happening. Think of it like trying to heat a giant ocean with a single cup of hot water.
So a Yi distortion is like a little nudge to the CMB's spectrum, not a big change.
Exactly. Now, mood distortions, those are different. They happen when Compton scattering is super efficient, driving the photons towards something we call kinetic equilibrium. It's like having a ton of those hot water cups, enough to really make a difference in the ocean's temperature.
Okay, so a mu distortion is a more noticeable change. And like you said before, the type of distortion we see, or don't see, tells us something about when and how energy was added to or taken away from the early universe. It's like the CMB spectrum keeps a record of these early events.
Yeah, it's like a chronicle, a cosmic chronicle, written in the subtle details of the CMB spectrum. It's pretty amazing when you think about it. Let's get a bit deeper into these distortions, shall we? Let's start with the Y distortion.
Sounds good to me. Can you tell me more about what makes a wide distortion unique? What does it tell us about the universe?
Sure. Like we talked about before, a Y distortion happens when the energy transfer between photons and electrons through Compton scattering isn't very efficient. This usually means there aren't that many scatterings going on, so the energy transfer per scattering is pretty small. Imagine like giving a giant boulder a tiny nudge. It might move a little, but the overall effect isn't huge.
So the energy transfer in a Y distortion is like a bunch of tiny little nudges, leading to a small change in the photon's energy. But how do we measure how big this distortion is?
We use something called, well, it's cleverly named, the Y parameter. It basically tells us how many scatterings are happening and how much energy is being exchanged per scattering. A higher Y parameter means a bigger distortion in the CMB spectrum.
And if I remember right, a higher Y parameter means more energy is going from electrons to photons, heating them up, right?
You got it. Positive Y values tell us that electrons are giving energy to photons, making them hotter. Negative Y values mean the photons are actually cooling the electrons. But in the early universe, those positive Y distortions are way more common since most things were heating up back then.
That makes sense. So Y distortions, even though they're small, they give us valuable information about the energy flow in the early universe. Are there any, real-world examples where we see these Y distortions?
Oh, absolutely. A great example is the Sunyaev-Zaldovich effect. It happens when CMB photons pass through the hot gas in galaxy clusters. The electrons in that gas are really energetic, and they give the photons a little energy boost, which creates a detectable Y distortion.
So these distortions aren't just theoretical, they have real observable effects. That's pretty neat.
It is, isn't it? Now let's switch gears a bit and talk about the mu distortion, which happens under very different circumstances.
I'm all ears. Tell me more about the mu distortion and what makes it different from the Y distortion.
Well, we said earlier that mu distortions appear when Compton scattering is working at peak efficiency, basically forcing those photons into a state we call kinetic equilibrium. It's like a constant back and forth energy exchange between photons and electrons, trying to find a balance. But you brought up a good point earlier. Compton scattering keeps the number of photons the same. So how do we get to a true black body, a state of complete equilibrium, if the number of photons stays constant?
That's something I've been wondering about too. If Compton scattering is just shuffling energy around without changing the photon count, how do we reach that equilibrium?
To answer that, we need to dive into Bose-Einstein statistics, the rules that govern how particles like photons, called bosons, behave. Unlike fermions, which follow the Pauli exclusion principle and can't be in the same quantum state, bosons can bunch up together in the same state. This love for togetherness allows them to have what's called a non-zero chemical potential, which might seem weird for particles like photons that don't have any mass.
A non-zero chemical potential for photons. That's interesting, especially since they don't have any mass to speak of. Can you explain more about this concept and how it connects to the mu distortion?
Of course. So in the early universe, photons can actually have this non-zero chemical potential, even though they're massless. It's a measure of how out of whack the number of photons is compared to the energy they carry. It tells us whether there are too many or too few photons compared to a perfect black body at a certain temperature.
So the chemical potential basically tells us how far off the photons are from a true black body equilibrium. It's a sign of whether there's a photon surplus or deficit given the temperature.
Exactly. A positive chemical potential means there are fewer photons than you'd expect in a black body at the same temperature, usually because some energy has been injected into the photon field. A negative chemical potential means there are more photons than expected, which usually means energy has been taken away.
And of course, a chemical potential of zero means we have a perfect black body, that perfect equilibrium we've been talking about.
Spot on. Now, going back to that mu distortion, during that time, the photons are behaving almost like they're in a Bose-Einstein state with a non-zero chemical potential. And it's this chemical potential, denoted by the Greek letter mu, that gives the mu distortion its name.
So it all comes down to the mu, this tiny indicator of how far the photons are from equilibrium. But like you mentioned earlier, even during this time when Compton scattering is super efficient, the mu distortion doesn't last forever, right?
That's right. Even though Compton scattering is dominating, the mu distortion eventually fades away. This happens because enough photons are created through processes like double Compton scattering and then get boosted up to higher energies. We call this smoothing out process thermalization, and it's actually super slow. It takes pretty much the entire age of the universe to get to that pristine black body spectrum we see today.
Wow, that's a really long time. It's amazing to think that the CMB has been on this journey toward equilibrium for billions of years. It really shows how the universe has slowly evolved over time. And this really long thermalization time means that the mu distortion gives us a super powerful way to look at events that happened in the very early universe. If we see a mu distortion today, we can be pretty sure it comes from a time when the universe was just a few thousand years old.
That's exactly right. It's like a time machine, letting us peek back into the universe's infancy. To figure out how much of a distortion survives from a certain time, we use something called the distortion visibility function.
Distortion visibility function, another interesting term. Can you tell me more about what that means?
Basically, it tells us how much of the energy that was injected at a particular redshift can still be seen as a distortion in the CMB today. It's a way of measuring how strongly a particular event has left its mark on the CMB's spectrum.
So, the distortion visibility function is like a measure of how memorable an event was in the CMB's history. Events that happened a really long time ago when the universe was super dense and hot, they get forgotten because of this efficient thermalization.
That's a great way to put it. The further back in time an event happened, the more likely is that its imprint has been smoothed away by thermalization. On the other hand, events that happened closer to the time of recombination, when the universe was cooler and less dense, those have a better chance of leaving a detectable mark.
This is fascinating. By carefully studying these distortions and how visible they are, we can piece together a timeline of when energy was added or taken away from the universe, as well as other important events. It's like the CMB spectrum is a cosmic history book, preserving traces of these ancient happenings.
It truly is. It's a remarkable demonstration of the power of physics, where even faint echoes from the distant past can be decoded from the subtle details of the CMB spectrum. But our journey isn't over yet. We've been talking about Y and mu distortions as if they're completely separate, but as you mentioned earlier, the transition between them isn't so abrupt.
Yeah, that's right. We've been treating them like they're in different boxes, but in reality, the shift between mu and U's distortions is more of a gradual change, right?
Exactly. The line between these two distortion types isn't sharp. It's more like a smooth, continuous transition. And this gradual change actually gives us even more information about the universe's thermal history. The shape of the distortion in this in-between zone tells us about when those energy release events happened.
So the distortion spectrum goes through a kind of metamorphosis over time. It's shape-changing as the universe expands and cools. And this gradual transformation captures the when, the timing of these energy injections.
You've got it. It's like each energy release event gets a timestamp, so we can see not only how much energy was involved, but also when it happened. To really capture this complexity, we need to go beyond those simple mu and yoi parameters and use what's called the thermalization Green's function, a powerful mathematical tool we touched on earlier.
The thermalization Green's function sounds like a pretty serious mathematical concept. Can you explain what it does and how it helps us understand the CMD spectrum?
This Green's function lets us accurately predict the distortion pattern for any energy release scenario you can think of. It takes into account the smooth transition between distortion types and all the details of the thermalization process.
So it's like a Rosetta Stone for the CMB spectrum. It helps us translate the complex language of the CMB into a story about the universe's thermal history. It connects our theoretical models to the actual data we observe.
That's a brilliant way to put it. It's a tool that allows us to rigorously test our understanding of the early universe against the evidence encoded in the CMB spectrum. We can use this Green's function to make precise predictions for different scenarios, like what the spectral imprint would be if a certain amount of energy was released at a specific time. Then we can compare these predictions to actual measurements from missions like COBE and other experiments.
It's like a cosmic detective game, isn't it?
Mhm.
We have the clues from the CMB spectrum, and we use the Green's function to see if any of our theoretical suspects match the evidence.
Exactly. It shows the power of the scientific method, where theoretical ideas are tested against real data, and our understanding of the universe gets refined step by step. Now, even though Kobe's measurements didn't find any big deviations from a blackbody spectrum, which suggests that the early universe was remarkably smooth, it doesn't mean these distortions are impossible to detect.
That's an important point. Just because Kobe didn't see these subtle distortions doesn't mean they're not there. Maybe future experiments with even better instruments will be able to uncover these hidden imprints.
That's the hope. Kobe was groundbreaking, but it was limited by the technology available at the time. Future missions like Pixie, PRISM, TMS, and others are designed to be way more sensitive. They could potentially detect distortions hundreds or even thousands of times fainter than Kobe could.
So we might be on the verge of discovering a whole new treasure trove of information about the early universe, hidden in these tiny spectral deviations. These next-generation experiments could totally revolutionize our understanding of cosmology, allowing us to probe times and events that were previously out of reach.
The possibilities are incredibly exciting. Just imagine gaining insights into the era of inflation, the birth of the first stars and galaxies, or even the mysteries of dark matter, all through the faint whispers of the CMB spectrum. Cosmologists are buzzing with anticipation.
It's amazing what scientists and engineers can do, constantly pushing the limits of what we can observe and learn about the universe. But before we get too carried away with all the exciting possibilities of future discoveries, let's remind ourselves about the well-established framework of the standard cosmological model, the lambda CDM model. What kinds of spectral distortions does this model predict, even without any exotic physics?
That's a great question. It's important to understand the distortions that are built into the standard model so we have a baseline to compare with. That way we can see if there are any signs of new physics lurking in the CMB spectrum.
Okay, so within lambda CDM, what are some of the distortions that we should definitely expect to see, even if there's nothing new or exotic going on?
One of the biggest sources of distortions in lambda CDM is the epoch of reionization. When those first stars and galaxies started shining, they bathed the universe in intense radiation, ionizing the neutral hydrogen gas that was everywhere in the early universe. This reionization process heated up the stuff between galaxies, creating hot electrons that scattered CMB photons, and that interaction left a mark on the CMB spectrum.
So reionization, which was a major turning point in the universe's evolution, would have left a Yo distortion signature on the CMB spectrum. It's like a cosmic fingerprint, marking the time when the universe went from neutral to ionized.
Precisely. How big this Y distortion is depends on the nitty-gritty details of the reionization process, which is something we're still actively researching. But current estimates suggest a Y parameter of something like a few times 10 to the minus 6. A tiny signal, but potentially detectable with upcoming experiments like PX-ray.
That's an incredibly small number, which shows just how hard it is to detect these subtle distortions. But if experiments like PXE work as well as we hope, we might actually see the spectral signature of reionization soon, opening a whole new window into this crucial period in the universe's history.
It's a prospect that has cosmologists on the edge of their seats. Now, moving on from reionization, another unavoidable source of distortions in lambda CDM is the damping of primordial density fluctuations.
Right, those density fluctuations are the seeds that eventually grew into the large-scale structure of the universe we see today. Galaxies, clusters, and all that.
Exactly. These fluctuations started out as quantum fluctuations in the very early universe and got stretched out to cosmological scales during inflation. But the fluctuations we see in the CMB's temperature map only represent the ones that survived until recombination. The ones on smaller scales, which correspond to higher frequencies, got damped out or erased before recombination happened.
Damped out. Can you explain how these small-scale fluctuations got erased?
It mainly happens through processes like photon diffusion. As these small-scale fluctuations dissipate, they add energy to the mix of photons and baryons, leaving a subtle mark on the CMB spectrum.
So even though these small-scale fluctuations were wiped out before recombination, the energy they injected into the photon-baryon fluid leaves behind a spectral distortion, a faint echo of their existence.
Exactly. This damping of small-scale fluctuations leads to a combination of mu and U distortions, and the exact mix depends on the scales involved. Really small-scale fluctuations mostly create mu distortions, while larger-scale fluctuations contribute more to Y distortions.
It's amazing how even the seemingly smooth CMB spectrum hides a record of these early density fluctuations. Their spectral signatures persist, even though they've been erased from the temperature map.
It really highlights the interconnectedness of all the physical processes happening in the early universe. Even things that seem fleeting can leave a lasting impact on the cosmic landscape.
This is all so captivating. We've talked about reionization, the damping of small-scale fluctuations, and they're both key events in the lambda CDM model. But what about recombination itself, the time when the first atoms formed? Didn't that big transition release a lot of energy too, maybe enough to leave its own spectral signature?
That's a sharp observation. You're right, cosmological recombination, the time when electrons and protons joined up to form neutral hydrogen atoms, produced its own unique set of spectral distortions. As these particles combined into atoms, they released photons. We call this the cosmological recombination radiation, or CRR for short.
So the CRR is like a spectral fingerprint of the recombination era, carrying detailed information about what was happening during that time. It's like a cosmic time capsule, preserving a snapshot of the universe as it transformed from the plasma into a neutral gas.
That's a beautiful way to describe it. The CRR spectrum has a series of distinct features, peaks and valleys, that correspond to the different atomic transitions involved in making those hydrogen atoms. These features depend on things like the baryon density, the abundance of helium, and the number of neutrino species.
So by carefully analyzing the CRR spectrum, we could potentially get independent measurements of these fundamental cosmological parameters, providing a valuable cross-check with other cosmological probes.
Exactly. The CRR gives us a unique and independent view of the recombination era, complementing other cosmological observations.
It seems like the CMB's spectrum is a rich tapestry woven from the threads of multiple cosmological processes, each leaving its own distinctive mark. It's a testament to the incredible power of spectroscopy as a tool for unraveling the history of the universe.
You said it. Every spectral feature, every little deviation from a perfect black body tells a story, offering a glimpse into a particular time or event. It's like a cosmic symphony waiting to be decoded.
This is truly awe-inspiring. We've discussed reionization, the damping of small-scale fluctuations, and the CRR, all major sources of spectral distortions within the lambda CDM model. But I remember you mentioning another, more subtle effect, the adiabatic cooling of baryons. Can you tell me more about that and how it might affect the CMB spectrum?
Of course. So as the universe expands, baryons, which include protons and neutrons, tend to cool down faster than photons. This happens because baryons can bump into each other through collisions, which is a very efficient way to spread their energy around. In contrast, photons, especially in the early universe, mostly just zip through space without interacting much.
So the baryons, kind of like a gas, can cool down more effectively through those collisions, while the photons, behaving more like individual particles, hold on to their energy more easily. This difference in cooling rates leads to a slight energy transfer from the photons to the baryons.
Exactly. It's as if the photons are giving up a tiny bit of their energy to help keep the baryons a little warmer. This energy transfer, though super small, shows up as a spectral distortion with negative mu and yi parameters. The amplitude is on the order of a few times 10 to the minus 9, which is incredibly tiny.
That's a really faint signal, practically a whisper, compared to the other distortions we've discussed. It seems unlikely that we'll be able to detect it directly with any of the experiments we have planned.
It's definitely a challenge to detect, given its tiny size. But it's still important to include it in our calculations to make sure we have a complete picture. It's a reminder that even the smallest processes can leave an imprint on the CMB spectrum, showing just how sensitive this cosmic probe is.
It really highlights the interconnectedness of everything happening in the early universe. Even seemingly insignificant events can have subtle but measurable consequences. So we've covered a lot of ground talking about the spectral distortions predicted by the standard lambda CDM model. But what about the possibility of new physics? Could these distortions also give us hints about things that go beyond our current understanding of the universe?
That's a question that's at the very forefront of cosmological research. While lambda CDM has been remarkably successful in explaining a wide range of observations, we know it's not the whole story. There are still big mysteries out there, like the nature of dark matter, the origin of the universe's accelerated expansion, and the physics of inflation. And these mysteries could potentially leave their fingerprints on the CMB spectrum, just waiting for us to decode them.
So the CMB spectrum, because it's so sensitive to processes in the early universe, could act as a window into new physics, revealing things that go beyond what we currently understand. That's pretty exciting. It reminds us that we're still exploring the frontiers of knowledge.
It really is. Spectral distortions are a unique tool for exploring new physics, providing insights into processes that occurred in the very early universe, long before the first stars and galaxies even formed. For instance, some dark matter models suggest that dark matter particles could annihilate or decay, releasing energy into the photon baryon fluid and potentially leaving a detectable spectral distortion behind.
So by carefully studying the CMB spectrum, we might be able to indirectly detect dark matter, or at least narrow down its properties. It's a tantalizing thought, a reminder that the universe still holds many secrets waiting to be discovered.
Exactly, and that's just one example. There are lots of scenarios involving new physics that could leave their marks on the CMB spectrum, each with its own unique signature. The possibilities are vast and incredibly exciting, pushing cosmologists to refine their observations and theories further.
It sounds like we're at the beginning of a new era in cosmology, where the CMB spectrum, which we once thought was smooth and featureless, is becoming a powerful tool for probing the fundamental nature of the universe. The whispers of spectral distortions could guide us towards a deeper understanding of the cosmos and its underlying laws.
It's a truly exciting time to be a cosmologist. With new experiments coming online and theoretical models constantly improving, we're poised to unlock a wealth of information about the universe's earliest moments and potentially uncover new physics beyond our wildest dreams.
This is mind-blowing stuff. It's incredible how a seemingly simple observation, the CMB spectrum, can have such profound implications for our understanding of the universe. But before we get completely swept away by the possibilities of future discoveries, let's take a moment to acknowledge the huge challenges involved in observing these subtle distortions.
You're absolutely right. It's easy to get excited about potential discoveries, but it's crucial to remember that measuring these tiny signals is an incredibly difficult task. There are technical and observational hurdles to overcome.
What are some of the biggest challenges that stand in the way of detecting and analyzing these subtle spectral distortions?
One major obstacle is foreground contamination. The CMB isn't the only source of radiation in the sky. There are tons of astrophysical objects out there, galaxies, stars, dust clouds, all emitting their own radiation, creating a complex web of signals that can drown out the faint whispers of the CMB's distortions.
So it's like trying to hear a quiet whisper in a noisy room. Those foreground signals, which are often much brighter than the CMB distortions, can easily overwhelm our detectors, making it really tough to isolate the signals we're interested in.
That's exactly it. It's a constant battle against a cosmic symphony of noise. We need to come up with clever techniques to effectively separate those foreground signals from the subtle distortions we're trying to find.
What kind of strategies do scientists use to deal with this massive problem of foreground contamination?
One approach is to observe the sky over a wide range of frequencies. Different astrophysical objects emit radiation with distinct spectral signatures. By observing at multiple frequencies, we can try to separate the contributions from different foreground sources and isolate the pristine CMB signal.
So it's kind of like using a prism to split white light into its different colors, each color representing a different astrophysical source. By looking at the spectrum across a wide range of frequencies, we can try to tease apart the contributions from these very sources and get the pure CMB signal.
That's a great analogy. Another strategy is to meticulously map out known foreground sources and use that information to model their contribution to the observed signal. This requires detailed observations of the sky at various wavelengths, combined with sophisticated modeling techniques to accurately predict and subtract the foreground contribution.
It sounds like a very delicate process, a dance between observation and computation, where we're constantly refining our understanding of both the foreground sources and the instruments we use to observe them.
It is indeed. It's a challenging task, requiring both clever observation strategies and powerful computational tools. Even with these advanced techniques, foreground contamination remains a major challenge in CMB spectral distortion science. But the good news is that the scientific community is constantly developing new and better methods for dealing with foregrounds, pushing the limits of what's possible.
That's encouraging to hear. It's inspiring to see scientists constantly innovating, finding new ways to overcome obstacles that stand in the way of discovery. Besides foreground contamination, are there any other challenges that make it difficult to study these elusive spectral distortions?
Another big one is instrumental calibration. Remember, we're looking for distortions that are tiny fractions of the total CMB signal, which means we need instruments that are incredibly precise and stable to detect these faint variations. Even a small error in our measurements could completely hide the distortions we're looking for.
So the pursuit of precision is absolutely essential in this field. Even a tiny calibration error could sabotage our efforts, obscuring the subtle signals we're trying so hard to uncover.
You got it. Calibration is crucial. We need to be absolutely sure that any signal we detect is real, not just an artifact of our instruments. To achieve that level of calibration, we need meticulous design, rigorous testing, and constant cross-checking.
What steps do scientists take to ensure that level of precision, that absolute confidence in the measurements?
It's a multi-pronged approach. It involves careful instrument design, using highly stable reference sources for calibration, and rigorously comparing data from multiple detectors and experiments to check for consistency. It's a meticulous and demanding process where attention to detail is everything.
It really highlights the dedication and rigor of the scientific community, this relentless pursuit of accuracy and reliability in our quest to understand the universe.
Absolutely. There's no room for complacency or shortcuts when we're dealing with signals this faint. Every step, from designing the instruments to analyzing the data, must be done with the utmost care and precision.
I'm starting to get a sense of the immense challenges involved in this research, the dedication and ingenuity required to extract these faint whispers from the cosmic background. It's truly awe-inspiring.
It is challenging, but the potential rewards are enormous. If we can overcome these hurdles and unlock the secrets embedded within the CMB spectrum, we'll gain profound new insights into the universe's beginnings, its evolution, and the fundamental laws that govern its existence.
The stakes are high, the challenges are formidable, but the potential payoff is truly revolutionary. I'm eager to learn more about the specific experiments that are planned or underway to address these challenges, to hear about the cutting-edge technology and innovative approaches being used in this exciting field of research.
That's a perfect transition to our next topic. Let's explore the exciting future of CMB spectral distortion science, where human ingenuity meets cosmic exploration.
So we're standing at the edge of this new era of exploration. What are the big missions and experiments that have cosmologists so excited?
One that's getting a lot of attention is PIXI, the Primordial Inflation Explorer. It's a proposed NASA mission that wants to use a Fourier transform spectrometer, kind of like COBE's FIRIS instrument, but way more sensitive.
So basically a next-gen Kobe with the tools to see even deeper into the CMB spectrum, those subtle details.
Exactly. PIXI is designed to be so sensitive that it could pick up distortions hundreds of times fainter than what COBE could see. That would open up a whole new world of signals we couldn't access before. Plus, it would cover a wider range of frequencies, which would make it much easier to separate foreground contamination from the real CMB signal.
That's a huge leap forward in our observational capabilities. What kind of amazing science could PIXI do if it gets approved?
PIXI has the potential to completely change how we understand the early universe. It could detect those super faint spectral distortions from the damping of primordial density fluctuations, which would be a direct test of inflationary models, that theory about the universe's rapid expansion in the first tiny fraction of a second.
Wow, a direct probe of inflation. That period was so short, but so important for shaping the universe we live in. It's an incredible thought.
It is, isn't it? And on top of that, PXIE could measure the spectrum of the cosmological recombination radiation with incredible precision, giving us new insights into the physics of recombination, that era when the first atoms formed.
So PXC is like a multi-tool, a cosmic Swiss Army knife that can tackle all sorts of fundamental questions about the early universe. It's really amazing what we can do with advancements in technology. It pushes the boundaries of what we can learn.
It really does. But while we wait for these ambitious space missions, are there any ground-based experiments making progress in CMB spectral distortion research right now?
That's a good question. What's happening on the ground?
Ground-based experiments have their challenges. You have to deal with atmospheric contamination and other limitations. But they're still really valuable because they complement the space missions. They're a faster and cheaper way to test out new technologies and refine our analysis techniques, which helps pave the way for future space-based experiments.
So they're like the scouts, going out ahead to explore the territory and prepare for the bigger missions.
That's a good way to think about it. One promising ground-based experiment is TMS, the Tenerife Microwave Spectrometer, which is located in the Canary Islands. TMS is specifically designed to look for low-frequency CMB spectral distortions, where the mu distortion from the damping of primordial density fluctuations should be strongest.
Detecting a primordial distortion from the ground would be a huge accomplishment.
Absolutely. TMS is still under development, but it has a lot of potential. Another ground-based project worth mentioning is BISO, the balloon-borne investigation of spectral offsets in the universe. This experiment is going to measure CMB spectral distortions from high above a good chunk of Earth's atmosphere, which helps reduce the problems caused by atmospheric contamination.
So it's like a high-altitude balloon, kind of a middle ground between the limitations of ground-based observations and the cost of a full-blown space mission.
Exactly. BISO's balloon platform gives it much better sensitivity than ground-based experiments, but it's still more affordable than sending a dedicated mission into space.
So it looks like the search for CMB spectral distortions is a multi-pronged effort, with space-based and ground-based experiments working together, each adding to our understanding of the universe.
That's right. This kind of teamwork, using different approaches, each with its own strengths and weaknesses, is how science moves forward.
As we wrap up this deep dive into the world of CMB spectral distortions, it's clear that this field is about to explode with new discoveries. With all these ambitious experiments coming up, both in space and on the ground, the next few decades promise incredible insights into the universe's earliest moments.
The CMB, which we once thought was just a simple leftover from the Big Bang, is now revealing itself to be a treasure chest of information. Its subtle whispers hold clues to the biggest questions about how the universe began and how it evolved.
It really shows the power of scientific curiosity, this drive to explore the cosmos in greater and greater detail, peeling back its layers to uncover its secrets.
And who knows what wonders await us as we continue to explore the CMB's spectrum. Maybe we'll find evidence of new particles, new forces, or even new dimensions, challenging everything we thought we knew about the universe and revealing a reality even more strange and beautiful than we could have imagined.
Or maybe these careful observations and analyses will further solidify our current models, confirming that our understanding of the universe is on the right track. Either way, it's the journey of exploration that truly matters, this constant pursuit of knowledge, pushing the limits of human understanding.
Couldn't have said it better myself. The universe is a vast and mysterious place, and we're just humble explorers, using our instruments and our minds to try and grasp its grandeur.
And to our listener, as we finish this deep dive, we leave you with this thought. What if the next whisper from the CMB, the next tiny change in its spectrum, reveals something that completely changes how we understand the cosmos? What if these faint echoes from the beginning of time hold the key to unlocking the universe's greatest mysteries? The search is on, and the answers might be closer than we think.